We're now going to talk about logarithms. And so logarithms are very much connected to exponential functions. They are actually the inverses of exponential functions. So we're going to start with what we're more familiar with, which is an exponential function, 4 to the x power. We've been asked to graph that, so we can always make a table of values. So for instance, if you plug in -2, 4 to the negative second power is the same thing as 1 over 4 squared, or 1/16. So at -2, 1/16, we are very, very close to the x-axis there, but we would have a point. If we plugged in -1, that's 4 to the negative first power, or 1/4. So we would have a point here. Plugging in 0, 4 to the 0 power is 1, so our y-intercept would be here at 1. We plug in 1, 4 to the first power is 4, so we'd have a point at 1/4. And then squaring 4, we would get out 16. So you also have a point way up here at 2/16. So we can graph that. And this goes, that's not the greatest graph. It's going to go up like this. And this is what we should have expected, right? We were expecting an increasing graph because we had a b value that was larger than 1. In this case, we would know that your domain was all real numbers. Your range was 0 to infinity, and your asymptote was a horizontal asymptote here at y equals 0. Now, we know a lot about inverse functions. We talked about that earlier this year. And knowing that with inverse functions, you're basically flip-flopping your x's and y's, then we can graph the inverse function of f of x at this point as well. And the best way to do that would be just by taking your table of values and literally flip-flopping your x's and y's. So that means that for our inverse function, all of the x's we would flip to have in our y column. So we would just have, instead of -2, 1/16, the -2 would be in your y's, and the 1/16 would be over here for your x's. So you would instead have the point 1/16 -2. So we could plot that. 1/16 would be right here, and -2 would be here. Then we would also have the point 1/4 -1. So 1/4 -1 would be right here. We would have the point 1, 0, which would be here. We would have the point 4, 1, so going 4 to the right and up 1. And then we would have the point 16, 2. So 16, 2 is going to be all the way over here. So this graph is now going to look like this. And if you remember, this is what happens if you were to reflect. So this was the inverse function, whereas this was the original function. But if you had reflected over the line y equals x, right, this line right here, then you would get your inverse function. So this is still a function, but what I can see here is our domain and our range and our asymptote is definitely going to be impacted by this. Think about if we know that your inverse function came about by flip-flopping your x's and y's, then it should make sense that the domain for your original function should now be the range of your inverse function. So now it's your range over here that is going to be all real numbers. But you can see that over here, you don't have any inputs that are negative, and you don't have any inputs at 0. So your inputs are now going to go from 0 to infinity. It's the domain because it's the range of the original. Again, the original had a horizontal asymptote here, right, at y equals 0. That was our asymptote. So if we're flip-flopping x's and y's, and that means now we have an asymptote for our inverse function that is x equals 0, right? We're flip-flopping x and y. So now x equals 0 means that we have actually a vertical asymptote here at x equals 0 for our inverse function. So what is the equation? Well, if we take our original function and we call it y equals 4 to the x power, remember our job is to basically solve for x here. But my question is, how do you solve for x? How do you isolate it? A lot of people say, oh, well, you need to take the xth root. Okay, well, if I take the xth root of each side, then all I'm going to get over here is 4 and then the xth root of y. I didn't isolate x. So in order to isolate x, we introduce logs. Okay, so if you have something where you're trying to, in this case, we were trying to get a variable that was currently as an exponent, we were trying to isolate it. So if we're trying to isolate this variable here, look at how these are related. A to the y power equals x is the same thing as y equaling log base a of x. These two, this is your exponential form, and this is your logarithmic form. Basically, what happens here is the base of your power becomes the base of your logarithm. The exponent here of your power is what your logarithm is equal to. And then the x here, which it was equal to, what your exponential form was equal to, is what your log base a is being taken of. So in this case, if we want to go back to this, the way that we're going to rewrite this to get this x, this exponent out, essentially what we can do is say, okay, this is log base, since the 4 is here, log base 4 of y equals x. So we have now isolated the x. And then remember, we need to flip-flop our x's and y's. So our inverse function is basically log base 4 of x equals y. So this function here is log base 4 of x. So the first thing you can do is just practice going back and forth between logarithmic and exponential functions. So if we have log base 3 of 81 equals 4, we're going to rewrite this in exponential form. Remember, whatever was the base for your logarithm is the base for your exponent or for your power. And then basically you're going to flip-flop what was by itself. So this is 3 to the 4th power. So this, which was by itself over here, becomes your exponent. And it's going to equal 81. Over here, 7 was your base, so it's the base of your power. This becomes the exponent, so 7 to the 1st power equals, and then whatever you had that you were taking the logarithm of, that's what your exponential equation is set equal to. In this case, you would have 14 to the 0 power equals 1. And over here, you would say 1/2, you need to put that in parentheses, to the negative 5th power equals 32. It's just as important going the other way. If you have the equation in exponential form, being able to write it in logarithmic. So in this case, we would say this is log, and then if this is the base of your exponent, it becomes the base of your logarithm. So log base 10 of the number that the equation, the exponential equation, was equal to is what you're going to take the logarithm of. And that should equal whatever you had for your exponent here becomes your answer over here. So log base 10 of 1,000 equals 3. Just as a side note, if you have a base 10, you can write this as log 1,000 equals 3. If the base is not written here, it's implied that it is 10. So you could write this either way. The next one, we would have log base 81 of 9 equals 1/2. Here we would have log base 2 of 1/8 equals -3. And then here we would have log base 8 of 1/8 equals -1. You might be asked to evaluate each logarithm. And I'm going to actually complete these in the next video because this takes just a little bit more explanation, and I don't want to make this video super long.